All right. So continuing on with chapter 9, well, I guess I'm going to review a tiny bit here of what we did yesterday. Can someone remind me? So here's our t equation. There's basically one difference between the t equation here and the z equation that we were dealing with in like chapter 7. What is the difference between this equation and the z equation?
It uses sample standard deviation instead of population.
Yep, right here, this S means sample standard deviation. In the Z equation, this is not an S, this is a sigma. The sigma means population standard deviation. This S means sample standard deviation. How is sample standard deviation, whose equation is shown right here, how is this different than population standard deviation? There's basically one difference between S, which is shown here, and sigma, which we started dealing with way in the early chapters of this course. What's the difference between this sample standard deviation and population standard deviation as far as the equation is concerned?
The denominator is n-1 for sample standard deviation.
Yep, and for population standard deviation, it is what?
Just n.
Yep, just n. Good. And I want to remind you that making the denominator bigger, making this number smaller, makes the entire standard deviation bigger because you're dividing by a smaller number. When the denominator gets smaller, that causes the overall standard deviation to be bigger, which causes the overall estimated standard error to be bigger, which causes the final t-value that you would calculate to be smaller. As estimated standard error gets bigger, the overall t gets smaller, or that is, the t-value gets closer to 0. As the t-value gets closer to 0, are you more likely to reject the null hypothesis, or are you more likely to accept the null hypothesis? As the t-value approaches 0, are you more likely to accept the null hypothesis or more likely to reject the null hypothesis?
Accept the null hypothesis.
That is right. Accept the null hypothesis is that, remember, basically what we're doing is we're taking this t-value and we conclude that there's a significant difference if it's really far away from 0, if it's way off in one of the tails. But if you make the standard deviation bigger, which makes the estimated standard error bigger, which makes the overall t smaller, that is closer to 0, what you're doing is you're moving this t-value closer to the center of the distribution. The closer it is to the center of the distribution, the more likely you are to accept the null hypothesis. That is, the more likely you are to say there is not a significant difference between our sample mean, which is this m right here, and our population mean, which is our mu right there. Let's see. Yeah, degrees of freedom's n-1. T-table. Yeah, so yesterday, let's go to our example from yesterday. We did this example from yesterday, and I want to continue. We did this, we assumed yesterday that this was a two-tailed test. So kind of reminding you of what this example was. We had infants, babies. We were measuring their looking time. Each baby stared at a computer screen for 20 seconds. Half the screen had an attractive face. On the other half of the screen had an unattractive face. And we were measuring the proportion of the 20 seconds, basically, that each baby was looking at each face. And our null hypothesis for this study, assuming it was a two-tailed test, our null hypothesis for this study was mu of the mu in parentheses attractive equals 10 seconds. And I mentioned last time that in the one sample t-test, you're very often inferring the population mean based on rules of probability. Does anyone remember how did we get mathematically, how did we get that, that number 10, which appears in the null hypothesis? Once again, the null hypothesis is the mu of the looking time for the attractive faces will be 10 seconds. How did we get that? You can either describe it in words, or if you want to describe it like mathematically, either answer is acceptable. How did we get that mu attractive equals 10 seconds?
We divided 20 by 2 because then the infant would be looking at the attractive person and the non-attractive face for the same amount of time.
Exactly. We divided 20 by 2, or we multiplied it by 50%, which is the same thing as dividing by 2. So yeah, dividing 20 by 2, which is basically the infant's performance if it does not show a preference for either type of face. If it looks equally long at each face, then it will be looking at the attractive face for 10 seconds. So our null hypothesis was mu, in parentheses, attractive equals 10 seconds. Our research hypothesis would be mu does not equal, mu, parentheses, attractive does not equal 10 seconds, which would be considered a two-tailed hypothesis test because there are two different things that could satisfy this sentence or the equation. Mu attractive does not equal 10, and one of those things is mu attractive is greater than 10. The other one is mu attractive is less than 10. When you say mu does not equal 10, that kind of means two different things. Mu is greater than 10 or mu is less than 10. Mu attractive is greater than 10, mu attractive is less than 10. And so I want to review in particular. So we calculate, I guess we should, I'll just show you I worked the math out for you, so I'm not going to go through it again, but I'll just remind you, we had, the sample mean, the standard deviation right here, the standard error, we needed to calculate the t, we needed to calculate, and those calculations are all right here. One thing I want to point out is that when we're calculating sample standard deviation, which I don't think you're going to have to do on the test actually, you're dividing, the denominator is n minus 1. So that's sample standard deviation where the denominator is n minus 1. For estimated standard error, I want to point out that the denominator is still n. It's the square root of n. Goodness. Happy fingers today. Okay, this thing right here is this number 9 is just n. And the denominator up here, it's n minus 1 for the sample standard deviation. For the estimated standard error, you're not subtracting by 1, it's just n. Sample standard deviation divided by the square root of n. N was 9, which is why that number is there. So I worked those out for you last time. We also had to, one of the skills in this chapter is using your t-table. One of the skills in this chapter is using your t-table to find the critical t values. So if alpha equals 0.05 and alpha equals 0.01, those were the two those are the two alpha levels that we used last time. Remember, if I say alpha equals 0.05, well, someone answer me. If alpha is 0.05, what percentage of area is to the right what percentage is in each individual tail? If alpha equals 5%, what percentage of the distribution is in only one of the tails? Can anyone tell me that? Is in only one of the two tails, if alpha equals 0.05.
2.5%.
Yep, 2.5% is correct. Remember, when you have a two-tailed test, you're dividing the total alpha by 2, and that is the amount of area in each of the tails. And similarly, when our alpha was 0.01, there would be 0.5% in each tail. There's two tails, each one with 0.5%, which totals alpha equals 0.01, or alpha equals 1%. If we actually look up, so remember whenever you're looking at t-table, I guess I should show you the t-table real quick. Here's the t-table. Whenever you're using this t-table, you need to know your degrees of freedom. In the current example, our degrees of freedom are 8. You need to know whether it's one tail, which is the top line, or two tails, which is the bottom line. And then you also need to know the alpha level, which in one of the examples was 0.05 for us. The other example was 0.01. So I already mentioned, or I haven't mentioned, but I mentioned last time. When alpha was 0.05, two tails, degrees of freedom equals 8. Our critical t was 2.306. Let's remind ourselves why that's the right answer. So degrees of freedom 8 is right here. we're doing two tails with alpha equals 0.05. So this number right here, you go to where they intersect. Right here, those numbers intersect 2.306. That is the critical T for a two-tailed test, degrees of freedom 8 with alpha equals 0.05. If we are doing alpha equals 0.01 two tails, which means 1% total in both tails, 0.5% in each tail, degrees of freedom 8, two tails, then it says there 3.355. Let's prove that to ourselves. There's degrees of freedom 8. We're going to where it says 0.01 in the two tails row, scroll down, 3.355. That is the critical T for alpha equals 0.01, two-tailed test, degrees of freedom equals 8. And so once you have we calculated the T, this is the T that corresponds to our sample mean. This T right here of 3 corresponds to the T for our sample mean. These things right here, these vertical lines, these correspond to the critical T. The shaded region, which I didn't actually shade it in this drawing, but the tails, those correspond to the critical region. Our 3 in this case is in the critical region when alpha equals 0.05. So what would we decide to do here? Accept the null hypothesis or reject the null hypothesis? Our T is in this tail. It is in the critical region. Therefore, should we accept or reject the null hypothesis?
Reject the null hypothesis.
Thank you. It is a rejection. You should be rejecting the null hypothesis because 3 is in this tail. And that's why it's helpful to draw these distributions, put one critical T over here, the other critical T over here, then draw in where your actual calculated T value is. Remember, up here we calculated T equals 3 right here. That's where we're getting this number 3 right here. 3 is in the critical region because it's in this right tail right here. Therefore, we would reject the null hypothesis. We would conclude that the sample mean that corresponds to T, that sample mean was 13, is significantly different than the hypothetical population mean, which was 10. This is assuming alpha equals 0.05. There's a different story if we use a more stringent, a more conservative alpha, which would be alpha equals 0.01, which is what is shown here. When alpha equals 0.01, I just showed you this in the T table, the critical T value was 3.355. So we got negative 3.355 on the negative side of the distribution. Right here, this vertical line is the positive critical T, 3.355 right here. And that same, if we're using an alpha of 0.01, which is a more stringent alpha level, it's more difficult to find statistical significance here. You notice that the 3 is not in the critical region here. So the 3, we would have to accept the null hypothesis right here. We would say that there is not a statistically significant difference because the 3 is not in either of the critical regions. The 3 did not make it as far out as those two tails, either of the two tails. It is inside this area right here, which is not the critical region. The critical region are these two tails. They're two parts beyond the critical T's and the tails, the critical region. Okay, so that was a two-tailed test. So right here, this is a two-tailed test. Now, I just want to make sure that we could conceptualize the same problem as a one-tailed test. And it's not really difficult to imagine this as a one-tailed test. So remember, you use a one-tailed test when your hypothesis, your research hypothesis in particular, says, I am only willing to even consider that there could be, that the sample mean will differ in one direction, either up, greater than or less than the population mean. The sample mean, for instance, for attractive faces, if you are a researcher, you might say, it is inconceivable that an infant would spend less time looking at attractive face. So we won't even consider that. Our hypothesis is that if infants can differentiate between attractive and unattractive faces, the direction of the effect will be that infants will look at the attractive face more. That's a reasonable hypothesis, and it's a one-tailed hypothesis because you're not even considering the possibility that infants would spend less time than 10 seconds looking at the attractive face. That is to say, you won't even consider the possibility that infants will spend more time looking at the unattractive face in the computer screen. You won't even consider that as a potential outcome of the study. You're only considering your research hypothesis to be infants will spend more time looking at the attractive face. If you do that, what it asks here, what are the null hypothesis and what are the research hypothesis? There they are, right there. So please notice now that when we have a one-tailed test, this changes the way our null and research hypothesis would be. Where this is the same question, but now we're pretending it's a one-tailed test. Now we're pretending that we have a research hypothesis that predicts that attractive faces can only show greater amount of time looking at them. There's no way, it's impossible, it's inconceivable that the babies would spend less time than 10 seconds looking at the attractive face. So that's the null hypothesis. The null hypothesis right here is the amount of time the infants will spend looking at the attractive face is equal to 10 seconds or less than 10 seconds. That is the null hypothesis. It includes all of the different possibilities that you think basically are unlikely, that cannot happen. You know, if any of these things basically said there's no effect, no matter what, this is the situations in which we will conclude that there is no effect in the study. But the research hypothesis here, this is where you can really tell it's a one-tailed test, because when we were pretending that this example was a two-tailed test, the research hypothesis was mu attractive does not equal 10, which I mentioned which means two things. It means either mu attractive is greater than 10 or mu attractive is less than 10. But here, there's only one of those tails is present. And that tail right here is mu attractive is greater than 10. We only have the one side of the distribution here. So that's how you can tell that it's a one-tailed test, because we only see one inequality here. It's only one side of the distribution right there. So now I want us to find some of these. Let's start with alpha equals 0.1. So I want you guys to look up on your T table. You could cheat if you really want to. The alpha is in the notes portion, but I really want you to try and do this for practice, because you will need to do this, not on the test this Friday, but in the test in the future. You will need to be able to find these critical T values using the T table. So go ahead, start using your T table. The degrees of freedom are 8. One-tailed test, our alpha level is 0.1 or 10%. 0.1 or 10%. Someone tell me what the critical T would be for one-tailed test, degrees of freedom 8, and the alpha level is 0.1. I will do the same. Does anyone think they have the correct answer? Degrees of freedom 8. One-tailed test, alpha equals 0.1. What is our critical T? Go ahead and call it out, someone, when you think you know what the critical T is.
Is it 1.397?
That is it, right here. This thing right here. The degrees of freedom is 8, right there. Up here, we go to the one-tail row now, and there, this is the alpha level 0.1. We go to where the 8 intersects with this right here, the alpha 0.1 in the one-tail test, and that's right there, 1.397. Now let's go ahead. I want you guys to do the same thing, but do it for alpha equals 0.01. So it's still degrees of freedom equals 8. It's still a one-tailed test, but now we're going to go to alpha level equals 0.01. What is the critical T there?
2.896.
Good. 2.896, which is right here. Degrees of freedom is 8. You go all the way over there. This is 0.01 up here in the one-tailed row right here. Go to where they intersect. Right here, we have 2.896. And I've actually made a picture for this one. Remember, we're still using the same t value. We're still going all the way back to, the way we calculated t last time, which is right here. The sample mean's 13. The population mean, we're still assuming is 10. The estimated standard error was still 1. The t value is still 3. The only thing that has changed is the fact that we have one tail, and our alpha level is 0.01 in this example. And so this is how we would draw that. Please notice, by the way, how we only have one tail that's considered a critical region. We don't have anything over here anymore because this is a one-tailed test. All 5% of the alpha, all 5% are in this one tail. Instead of having 2.5% over here and 2.5% over here, when you're doing a one-tailed test, all 5% is right here. So our t of 3 is in the critical region here. So if we do a one-tailed test with alpha equals 0.01, we would reject the null hypothesis because 3 is greater than 2.896. That is, 3 is in this, this critical region right here. 3 is greater than the critical t. Any questions or comments about one-tailed test and how they differ from two-tailed tests? Okay. So let's see. What we have here is another example of a one-sample t-test. And I haven't done the, yeah, this is just, let me look at the notes portion here. Yeah, I assume for this one, mu is equal or less than, yeah. Shoot. We're going to assume that this is a one-tailed test. I kind of typoed there and then said two tails. Assume this is a one-tailed test. Yeah, erase this as well. We'll assume that this is a one-tailed test right here. The main reason I included this example was because I wanted us to get a little bit more practice calculating or seeing how to calculate sample standard deviation and how to calculate t. And so we have the data set A right here. We just it's a small sample size of 5 right here. And these are scores on a test. And the scores on the test, there are 10 questions. Each one is a true-false question. And does anyone know, what is the probability on a true-false question? What is the probability of guessing right on any given problem?
50%.
It is 50%. And so this once again, there's 10 true-false questions. And the question we're basically asking here is, these are scores of students on this test or on this quiz. And the basic question we're asking here is participants' performance on this test better than just random guessing? If the students were just random guessing, and there's 10 questions on this test, and if they were just randomly guessing, how many questions on average would you expect those students to get right? If there's 10 questions and the rate of, if 50% of the time you'll get a question right, how many questions would you think on average students would get if they were just randomly guessing?
5.
5 is correct. And this is, once again, we're discovering, or we're inferring the population mean using probability theory. In this case, we're taking the total amount of questions, 10, and multiplying it times 50%, or dividing it by 2, because there's 2 answer choices on each problem, true or false. If you're just randomly guessing, you have a 50% chance of getting it right. So 10 divided by 2 equals 5, or 10 times 50% equals 5. That is going to be our hypothetical population mean in this problem, which is right here. Our sample mean is 6. So if you add up all these numbers right here, 5 plus 6, 18, 23, these things equal 30. 30 divided by 5 equals 6. So this is our sample mean. The actual average score on the test was 6 out of 10 questions correct. Chance performance, that is, if the students were just guessing, you would have guessed that they would get 5. Our question is are these two numbers significantly different from each other? Is 6 significantly different than 5? And so this is how you set up the t equation. 6 minus 5 is the numerator. The standard deviation, the sample standard deviation happens to be 1. Where does this number 5 come from?
That's in the number of
That-
participants.
Yep, that is the sample size. And this is the denominator of the t equation is estimated standard error. And so this is how you set up the t equation here, 2.236. And just to show you, I've actually calculated the sample standard deviation for this one. It says 1 squared, 0 squared, 1 squared, 1 squared, 1 squared. Just to remind you why we get those. 5 minus 6 squared, that would be 1 squared right there. 6 minus 6 is 0 squared. 7 minus 6, 1 squared. 1 squared, 1 squared. This just comes from taking each one of these numbers and then squaring it. And you get these things right here. When you add those things up, 1, 2, 3, 4, divided by 4, that gives you 4 divided by 4 equals 1. The square root of 1 equals 1. So this is how we get the sample standard deviation. The thing I want to point out once again, though, is notice how when we're calculating standard deviation, we're taking the sample size minus 1. However, when we're calculating the estimated standard error, we're still using the full sample size of 5. That's a common error. Please note, is the sample standard deviation that has n minus 1 in the denominator. Right here, the estimated standard error is the full n equals 5. So you could look up, I don't feel like you guys are having too much problem looking up critical t values. If you assume it's a two-tailed test versus assuming it's a one-tailed test, you could determine whether this t value right here is in the critical region. Oh, I guess we could do one just right now. Let's say that we're doing this. Let's say that we're using, let's say we're doing, we'll just make one up on the fly. Let's say we're doing alpha equals 0.01. And we're going to do a two-tailed test. Let's say we're doing alpha equals 0.01. And we're doing a two-tailed test. The degrees of freedom would be, what would our degrees of freedom be for this problem? What is the formula for degrees of freedom? And the formula is always the same. No one remembers how to calculate degrees of freedom?
Is it n minus 1?
Yep, so what is n right now? It is n minus 1, people. So what is the degrees of freedom going to be?
4.
4 is correct. 4 is the degrees of freedom. Let's assume we're going to do a two-tailed test with alpha equals 0.01. Let's go ahead and look that up. Let's see. So degrees of freedom equals 4. And then we're doing a two-tailed test. Alpha equals 0.01. Oh, goodness. That critical t is 4.604. So is this t right here, is this in the critical region? The critical t was 4.6. That critical t marks the boundaries into the tails, into the critical regions. Is this number in the tail, in one of the two tails?
No.
It is not, so we would accept the null hypothesis. That's assuming that we're doing a two-tailed test. Good. So that is it for chapter 9 stuff. So now we'll go over the test. Chapter 9 stuff for now. I guess we do have some, we'll doing paired samples t-tests next time. All right, so I'm going to turn off the sharing because I am going to be looking at the test. Oh, I cannot. Okay. Okay, so first thing about the test, the test is actually going to be two different little components on Blackboard. There's a multiple choice component, which is just going to be, the typical type of test we've taken. It's going to have around 30 questions, all multiple choice. And and then we will also have there's actually going to be a portion which is kind of like a written homework assignment where we're going to give you some problems and you're going to take pictures of your answers and you're going to submit them like you have been your written homework assignments. Take pictures of your assignments of the written portion of the test, copy and paste them into like a Microsoft Word document, and that will be what you submit for the written portion. And both of these things, I'll give you like 24 hours to take the tests starting, at the normal class time on Friday. So I'll give you basically a full day to take those tests because there's two parts, written and multiple choice. So let's go over the written portion first. Okay, so there will be a question. That's just the answers. I want to look at the actual test. Okay, for the written portion, you will have to do a two-tailed z-test using alpha equals 0.05. So you will be able to use your z-table, obviously, if you needed to. Though you really won't need to use the z-table for this problem, because if someone tell me if alpha equals 0.05 and you're doing a two-tailed z-test, what is the critical z?
1.96.
Yes, 1.96 is correct. So if that will be a problem where you'll basically be calculating z, where you have you'll be calculating a z for a sample mean. It looks like of a sample size of 27. You'll calculate that z and determine whether it's in the critical region or not using a critical z of plus or minus 1.96. And so we're going to assume it's a two-tailed test. Then you will also have to do a confidence interval for the same problem. So I gave you an example of confidence intervals in chapter 8, and it will be just like that. Like it will not be just different numbers, different like words and stuff. But the strategy for doing confidence interval is the exact same as the example I did in chapter 8. I'll remind you that when you're doing a confidence interval, the center of the distribution represents the sample mean. Whereas when you're doing the hypothesis test strategy, like in chapter 7, the center of the distribution was the population mean. That's really the primary difference. And you will be given the formulas, by the way, for confidence interval, and you will also be given the formula for z, how to calculate z for a sample mean. Though I still strongly suggest you practice the procedures themselves so you don't get stressed out and not be able to remember on the test. Finally, the third written portion for the test is you will have to calculate Cohen's d, our measure of effect size. So this test basically spans chapters 7 and 8. There's the main things in the written portion: hypothesis test, confidence interval, and Cohen's d are the three things that you'll be calculating. Any questions or comments about that aspect of things?
So is there not going to be anything from chapter 9, just z-test, no t-test?
Right, nothing. We will eventually have stuff on a test regarding the final test will have, I guess, 9, 10, and 11. 9, 10, and 11. But this test just only goes up to 8. There's nothing on T at all in this test. Anything else about the written portion? Okay, so now I'll kind of go through the questions for the multiple choice portion. There are definitely some probability problems, like where you're given a z-score. I'm looking at this very first problem here. You're given a z-score, and you either have to calculate the percentile, or you have to calculate the amount of area to the right of that z-score. What does percentile mean again? Someone tell me, what does percentile mean again?
Isn't it area to the left?
Yes. And so you have to know that on the test because it uses the word percentile on the test for some problems. And I don't want you to see that word and have no idea what it means. In the Z table that I gave you, the numbers in the middle of that Z table are the percentiles. They are the amount of the area to the left of a given Z score. Though for the particular problem I'm looking at, it's asking you to calculate the amount of area to the right, the amount of area greater than a given Z score. If you have to calculate the amount of area greater than a given Z score, what do you do using the table that I gave you to do that? What do you do at the percentile to calculate the amount of area to the right of a given Z score?
You subtract it from 1.
Yep, 1 minus the percentile gives you the amount of area to the right, or that is the amount of area greater than a given Z score. Good. You need to know the difference between an interval estimate and a point estimate. Yeah, here's the percentile question. So here's a question where you're going to have to convert a single score. So you have a single student. A single student, and you need to calculate the percentile of that student. The amount of area to the left of that student. Using, you have to calculate Z for the basic Z formula, where it's just sigma in the denominator. Here is a problem. Let's see, where where you need to calculate. It says, don't want to give too much information here. It's kind of like problem number 1 for the homework, where you kind of have to work backwards. Problem number 1 from homework 4, where you know that an individual is a certain percentile, and you need to use your Z table, knowing their percentile, to find out what their Z score is. And then once you know their Z score, you can calculate that individual's X value. So it's kind of like the homework for the first problem of the homework from homework 4, where you kind of work backwards. Oftentimes I'll give you the X value and then you'll convert that to the Z value. Here I give you the percentile, and then you use that to find the Z value, and then you use algebra to solve for X, which is basically exactly like that first problem, homework 4. Yeah, once again, this is a question about point estimate, interval estimate. You need to know the difference between parametric and non-parametric, those two terms. Here is a confidence interval question that's a multiple choice one. So this is a question where you basically have to calculate a confidence interval, and then it gives you 4 answer choices. One of the answer choices shows the correct confidence interval. So that's at least 2 confidence interval problems that you'll have to do on this test. Review the central limit theorem. There is a question about the central limit theorem on this test. Review what it says. I don't think it's a terrible idea to basically kind of memorize the central limit theorem. Know what sample size does to the size of your Z statistic. We did a demonstration with how the Z statistic and Cohen's D differ in the way that they are influenced by sample size. That was in chapter 8. So make sure you look at that. Know how sample size influences the Z statistic. There's a question about null and research hypotheses. I don't think that one will be particularly tough, though. I should say, just to be clear, I've been talking to a lot of groups about this. I'm not sure I'm going to keep this question on the test, but you reject the null hypothesis when P is less than alpha. We haven't actually talked too much about P, but that's a conceptual question. I've talked about it with some of the groups when we've had Zoom meetings. But when P is less than alpha, that is when you reject the null hypothesis. You always get a P less than alpha when your T is in the critical region. If your T is in the if your Z is in the critical region, that means your probability level, your P level is less than alpha. That's when you reject the null hypothesis. P is less than alpha. Know what Cohen's D, so know how to calculate it. Of course, you'll have the formula for Cohen's D, but also know what it means. Like Cohen's D is a measure of effect size, and it basically measures the amount of standard deviations that are separating the sample mean and the population mean. It tells you the amount of population standard deviations that are separating the sample mean and the population mean. Know when to use a one-tailed versus two-tailed test. There's a scenario problem where it gives you the person's research hypothesis, and you have to determine based on the wording of that research hypothesis whether you should use a one-tailed or two-tailed test. There's a problem here about Cohen's D. So it gives you those levels of small, medium, and large. And I should point out, if the level of small is 0.2, if you get a Cohen's D which is less than 0.2, then basically the effect size is considered negligible. If your Cohen's D, if your effect size is less than 0.2, then your effect size is considered basically negligible. There is no effect. Almost done here. Another question about one-tailed versus two-tailed tests. You should memorize the definition of statistical power. So we didn't do any calculations with statistical power, but you should just go ahead and memorize the definition. Here's a problem where you basically have to fill in 2 blanks from the definition of statistical power. Yeah, that's it. That's all the multiple choice questions I think you guys need help on. Are there any other questions or comments about this?
So is the actual multiple choice test itself timed, or
Yes.
is it?
They'll both be timed. I haven't decided on the amount of time for the written portion yet. I'll probably err on the side of giving you more time than you need for that. But for the multiple choice portion, I'll give you like an hour. And then the other one, there's only 3 problems for the written portion, but I'll probably still give you like 30 minutes at least for that, maybe probably more like 45 minutes for the written portion, actually. So I think I'm giving you way more time than you need. This is the test. Of course, I was warned about this test way when I started teaching this class. This is the test which back in the day, students would always use the full 50-minute period to do. Like there was always students who were like staying after the 50-minute period to finish this test when it was in class. But you guys won't have to worry about that. I'm going to give you'll have more than enough time to finish this test at home. Way more than you would if we were in person. Anything else? All right. I'm happy to stick around, and if you want to go over some problems or whatever, I have class at 10, but I can stick around and talk to you guys for a little bit until that next class starts if people want to. But I'm going to turn off my recording now.